All right, so we're working on chapter 2, lesson 6, special functions. So what we're going to learn today is we're going to learn how to identify and graph step functions, constant functions, and identity functions. We're also going to learn how to identify and graph absolute value and piecewise functions. So some vocabulary to keep in mind are step function, a greatest integer function, constant function, identity function, absolute value function, and piecewise function. So these are the things that we're going to be kind of engaging with and learning about in this lesson. So how do step functions apply to postal rates? So the cost of a postage to mail a letter is a function of weight of the letter. So, but the function is not linear, so it doesn't go up at a specific rate for each individual movement of x. So this type of special function is called this kind of special function is called a step function. And so if you notice here, we are dealing with, if it's between this weight and this weight, it costs this much. And if it's between this weight and this weight, it costs this much. And so there's a range of weight that it can be, and it's going to cost a specific amount before it steps up to the next level. And so there's lots of scenarios where we're going to deal with stuff like this. And these are going to be examples of step functions. So looking at step functions, constant functions, and identity functions, the graph of a step function is not linear, right? It doesn't make a line. It actually makes what you would expect a step. Okay, so you're going to see several steps as it goes. It consists of line segments or arrays, and the greatest integer function is written as f of x equals the greatest integer of x. So these special little symbols here, they almost look like two brackets together, is an example of a step function. Okay, so again, keeping in mind that these symbols on the outside are known as the greatest integer function. And so, for example, if we said, hey, what's the greatest integer of 7.3? That's 7, right? What's the greatest integer of negative 1.5? That's negative 2. So basically, you're always rounding down to the next greatest integer value. Looking at a graph, so if we were to study this table here, we say f of x equals the greatest integer of x. So if your x value is anything between negative 3 and negative 2, right? It's like negative 2.9, negative 2.6, negative 2.1, negative 2.0001, anything in between negative 3 and negative 2, it will always round down to the nearest greatest integer, which would be negative 3. All the values of x between negative 2 and negative 1 round to negative 2, and any x value between negative 1 and 0 rounds down, and so on and so forth, right? So basically, any x value within that range will always round down to the next greatest integer. So what does that look like? So here's an example of what the graph would look like. So each dot represents that the point is included in the graph. Each open dot or open circle means that the point is not included, right? So as my x values go from negative 4 to negative 3, right? They all round to negative 3, right? Anything from negative 3, or sorry, from negative 4 to from negative 3 to negative 2 round to negative 3, and so on and so forth, right? So any x value always rounds to that specific greatest integer. And that's why you see this step here. So this is an example of a step function. And again, just keeping in mind something you might not have a lot of experience with is this greatest integer symbol. And all that means is you're rounding that value down to its next, greatest integer, right? One thing to notice is the domain of a step function is typically all real numbers, right? So this could continue to be going left forever, right? Because I could input any x value, and it would go further to the right forever because I could input any x value in the positive direction or the negative direction, right? So my domain would be all real numbers because it would go left and right forever and ever. And the range is only the integers, right? If you notice, my y values are only ever going to be integers, right? I'm only going to have y value of like negative 1, 0, 1. There's nothing in between those integers that for y values that exist in this function. So let's look at a step function. So here's an example. It says labor costs at the Fix-It Auto Repair Shop are $60 per hour for any fraction thereof. So basically, if you roll into any part of the next hour, you get charged a full hour, right? So let's go ahead and draw a graph that represents the situation. So first thing, total labor charge must be a multiple of $60, right? Because they're charging per hour, and so they don't prorate. They don't do parts of an hour. You get charged for the whole hour, even if you only use a little bit of it. So this graph is going to be a step function. So if the time spent on labor is greater than 0 hours, but less than 1 hour, right? So anything between 0 and 1 hours, the labor cost will be $60. If your labor is between 1 hour and 2 hours, you're going to get charged $120 because anything in between there gets charged the full 2 hours, and so on and so forth. So let's go ahead and solve this. So we're going to use the pattern of time and cost to make a table, right? Where X is the number of hours of labor and C of X is the total cost of that labor. So here's the table here. So anything between 0 and 1 hours, right? 0 or equal to 1 hour is going to be $60. Anything that is more than 1 hour and less than or equal to 2 hours is $120. Anything that is greater than 2 but less than or equal to 3 is $180. And again, you can notice it's just going up by $60. And again, any X value between these two will make this cost. So what does that look like on a graph? It's going to be a step function, right? Anything between 0 and 1, right? So, and if someone spent 0 hours, obviously it's going to be 0, right? So that's why you see that open circle there. And so this step function would follow this exact table of values for that graph. So let's go ahead and examine. Since the shop rounds any fraction of an hour up to the next whole number, each segment on the graph has a circle at the left endpoint and a dot at the right endpoint, which is a little different than the greatest integer function that we looked at before, right? They always rounded down, where in this scenario, it always rounds up. So in lesson 2.4, we learned that the slope-intercept form of a linear equation is y equals mx plus b, right? And again, you probably had lots of experience with that, but it's going to keep coming back. So in functional notation, right? So this is standard notation. In functional notation, right, we have f of x. And again, m is still the slope, b is still the y-intercept, but instead of y, we have f of x, just to write it in functional notation. But if your slope is 0, right, that means that your steepness of your line is going to be completely horizontal, right? It makes a horizontal line, right? So if your slope is 0, 0 times x makes 0, which basically if your function will equal whatever your y-intercept is, because that would make sense, your horizontal line, right? So the function f of x equals b for every value of x, right? So f of x equals b is called a constant function because if you notice, if your slope is 0, it doesn't matter what your x value is, your function will always equal the same value. So what does that actually mean? Let's look at an example. So here it says graph f of x equals 3. So again, you notice that if I were to examine this slope-intercept form, it has no x value because the slope is 0, right? So it's this constant function here. And so what that means is for every value of x, right, no matter what value x is on the graph, my output will always be 3, right? My y value will always be 3. So here are my x values, and again, it didn't matter what my x value was, right? No matter what x is, my output or y value will always be 3. So what does that look like on a graph? It looks like this horizontal line. Again, no matter what my x value is left or right, my y value or my f of x value will always be 3, which makes a horizontal line. So another, let me just go back real quick. So this is an example of a constant function, right? So whenever you have just a constant, just a value, right, with no variable, it's going to make this horizontal line here. And so you're going to, obviously, if it was f of x equals -2, it would be a horizontal line down here. If it was f of x equals 0, it would be a horizontal line right along the x-axis, right? So Another special case of slope-intercept form is if the slope is 1, right? And the y-intercept of 0. So this creates the function f of x equals x, or y equals x. So the graph is aligned through the origin, right? Because our y-intercept is 0, and the slope is 1. So this would create a table like this, right? So basically, anytime I input an x value, it's going to match the exact same y value or the exact same output. So that creates a graph like this, right? So this would be where all your x values match exactly with your y values, creates a line with a slope of 1 and a y-intercept of 0. So this is what's known as an identity function. And the main reason why it's called an identity function is because the x and y values are identical, right? And that's what creates this line with a slope of 1 and a y-intercept of 0. So now we're going to talk about absolute value and piecewise functions. So an absolute value function would be an example of like f of x equals the absolute value of x. And so again, we're going to examine this. If we were to select some x values and put them into this function, right? The absolute value of -3 would be 3. The absolute value of -2 is 2. The absolute value of -1 is 1. The absolute value of 0 is 0. The absolute value of 1 is 1. And so you see this kind of pattern emerge. And so when you were to graph these coordinates on a graph, it would make this shape right here. It'd be like a V shape, right? Where I have -3, 3, -2, 2, -1, 1, 0, 0, 1, 1, 2, 2, 3, 3, right? And it makes kind of this V shape. That's what the absolute value functions will do. So absolute value functions can also be written as two pieces. If you notice, this is just a segment of a line or array that has a y-intercept of 0 and a slope of 1. This one is also an array that has a slope of -1 and a y-intercept of 0. And that's what this means. Basically, this absolute value function is just this piece and this piece, right? It would be this -1 slope with a y-intercept of 0 for all x values that are less than 0. And this one would be a line for a slope of +1, a y-intercept of 0 for all the x values that are equal to or greater than 0, right? So everything in this direction would be that +1 slope line with a y-intercept of 0. This would be a -1 slope line with a y-intercept of 0. So this function here, the absolute value of x, is identical to this function here that's the makeup of two different pieces of these lines, right? So you could either write it like this or you could write it like this. And so that's really going to introduce us into the idea of what is a piecewise function. And the only kind of weird thing when you're looking at piecewise functions is your piecewise function is just a combination of multiple pieces of multiple graphs all kind of graphed together. So let's dive into this a little bit more. So absolute value functions, right? So we have f of x equals the absolute value of x plus 1, and g of x equals the absolute value of x minus 2. So we're going to do them and graph them on the same coordinate and determine their similarities and differences. So first we're going to find the ordered pairs for each function. So here is the table for absolute value of x plus 1, right? So I'm going to pick some x values, plug them in, get my y values or my output values, right? Same thing for absolute value of x minus 2, right? Input your x values, right? And then get your y values or your output values. So now that I have my x and y coordinates, right, or my ordered pairs, I'm going to go ahead and graph the points. So this would be these points right here would be graphed, and it would make this, again, this V shape, right? That's what absolute value functions make. And then I would take these ordered pairs and I would make this V shape over here. Again, these are just the graph of these ordered pairs there. And so I can see that these two make the exact same shape. And if you notice, it's really similar to the original absolute value equation or function that went right through the origin. But if you notice, this one is actually just shifted up 1 unit, whereas this one is shifted down 2 units. And you can see that that's what happened when I took that absolute value function. And if I add 1, it moves it up 1. It gives it a vertical shift by 1 unit. Well, here, when I subtracted 2 to that same absolute value function, it shifted it down vertically 2 units. And those are the kind of things that we want to notice, right? The domain is still all real numbers, right? They both go to the left and to the right forever and ever and ever, both in the negative and positive direction. The range, right? Well, the range of this one, well, it includes all the numbers going in the positive direction, but stops at +1, right? So the range for this one would be for all the y values from +1 and greater, where this one would be the range would be all the values of y that are equal to -2 or greater, right? So this range are very similar, as in they both go to infinity, but this one has to be greater than or equal to +1, and this one has to be greater than or equal to -2. So the graphs have the same shape, but obviously different y-intercepts. This is a y-intercept of +1. This is a y-intercept of -2. And each one of the graphs is, again, it's just a translation, right? This one got shifted up 1 unit. This one got shifted down 2 units. And you can see in the equation what made that happen. So one thing you can also do is you can also use a graphing calculator to investigate these graphs as you're working through them. One thing that I would suggest is to use Desmos. You just type this into your web browser, desmos.com, and it'll take you to the graphing calculator. And here's where you can start to type in what graph or function you want to make, and it will actually make it for you, and it'll allow you to examine different types of graphs. It's really, really helpful when we're examining all the different types of functions we're working with, especially piecewise functions. And this is an example of a piecewise function. Here's one piece of it, right? Where things are separated by colons and commas. And if you want to see an example of this done in class, just ask your teacher, and we'll be happy to show you an example. Again, here's an example of how we type things out. Again, this is for all x values less than 2. It's going to graph the line x minus 4, and then it's separated by a comma to show the next one, the next piece, where for all values of x that are greater than or equal to 2, it's going to make a horizontal line at 1, right? So this would be like y equals x minus 4, y equals 1. So obviously that's a line with a slope of 1, y-intercept of -4. And y equals 1 would just be a horizontal line, right? And so that's what we're seeing here, right? Horizontal line at 1. Here's a diagonal line with a slope of 2 and a y-intercept of -4. Or sorry, slope of 1 and a y-intercept of -4. So let's look at piecewise functions, right? We want to examine these and see how they kind of play with each other. So here's a piecewise function. It says graph f of x equals x minus 4 if x is less than 2, and f of x equals 1 if x is greater than or equal to 2. And then it says identify the domain and range. So when I'm looking at this problem, recognize there are 2 pieces to this. This piece right here, and again, f of x equals x minus 4, this is a line, right, with a slope of 1 and a y-intercept of -4, right? F of x equals 1, again, that's a horizontal line, right? It'd be like y equals 1, it'd be a horizontal line at 1, which actually is the example that I just showed in the previous image. So first thing we want to do is we want to graph the line, right? Graph this line for only x values that are less than 2. Next, we want to, so this would be this line right here, right? So for x values less than 2, so obviously it cannot include 2, but everything less than that would be this diagonal line here, right, with a slope of 1 and a y-intercept of -4. And the next part would be to graph the second piece, right, this piece. So f of x equals 1, the horizontal line, for only x values that are greater than or equal to 2. And so it would look like this, right? So again, here's my horizontal line for only x values greater than or equal to 2. Here is that first piece, which is f of x equals x minus 4 for only values that are where x is less than 2. So again, this piecewise function is made up of these 2 pieces, right? And so this is the function that you're graphing, and then this is kind of its limitation of kind of where you're setting your x values for. So the function is defined for all values of x. So for this one, it will, it will have all the x values in the negative direction and the positive direction, because even at 2, it does have a value right there, right? So the domain for this one, for this piecewise function would be all real numbers. As far as the y coordinates go, it actually is limited, because if you notice, there are no y values between -2 and +1, right? So here I would say that my range would be for all values that are for where y is less than -2, and for all values of y equal to 1, right? If you notice, there's nothing above 1, there's nothing below 1, right? So for all y values that are less than 2 or equal to 1. So here's a little tip here. So when you're examining the graphs of piecewise functions, each part of the piecewise function may or may not connect, right? So in this instance here, they don't connect. In some instances, they may connect. They don't have to. It's just whatever the parameters are of the piecewise function. So just keep that in mind as you're working through these. So let's examine the special functions that we've talked about. So remember the step function, right? It has horizontal segments and rays, right? So again, it looks like a step. We have the constant function, which is just a horizontal line, right? So like f of x equals a constant, a number like f of x equals 4, or f of x equals -2. We have the absolute value function, which looks like a v, right? Which can be shifted. And then we have a piecewise function, which can be made up of multiple pieces, right? It can be made up of diagonal line, a horizontal line, another diagonal line. So this would be a piecewise function that has 3 pieces to it. You can see in our previous example, we had a piecewise function that had 2 pieces to it. So let's identify some of these functions here. So if we were presented with this and it says determine whether each graph represents a step function, a constant function, or an absolute value function, or a piecewise function, what are they? Well, here we can see for A that this would be a piecewise function, right? Or sorry, a step function. So this step function, right, it creates the step, right? Since the graph consists of multiple horizontal segments, it represents a step function. If I look at this one, I see just a horizontal line going on forever in both directions. So that would be an example of a constant function, right? So this would be kind of an easy way of being able to tell. Again, if you kind of need a point of reference, this is a kind of an easy way to reference what type of function it is. All right, thank you guys for watching. Let me know if you guys have any questions.